Hey folks, how you doing? Don Grant, CTC, Cutting Tool Counselor, here with another exciting episode of In the Loop TV, sponsored by Harvey Performance Company. Thanks for coming back. Real quick formality, like we always do, subscribe, like, that would be great. I would much appreciate that. So thanks for doing that. If you are subscribed and liked, hey, thanks for being part of the Cutting Tool Counselor militia. We like it, and thanks for coming back. What are we talking about? Well, we're doing a series of high efficiency machining, and we're talking about the things that a high efficiency, dynamic, some people know it as dynamic, a dynamic tool path does to take care of our cutting tool. Two things, folks. We're gonna start on this one. Two things that are going to kill our cutting tools that we need to take care of, and that's what high efficiency does. And those two things are heat, we gotta control that, and vibration. We have to control that. So we're gonna talk on this episode how a high efficiency tool path takes care of the heat and takes care of the vibration to put our tool in such a wonderful, fun, lovable spot so we can be efficient at our tool path. Again, high efficiency. It's all about the efficiency. So join me, not now, we gotta do this little intro thing, but you can join me next. Well, hey folks, thanks for coming back. We're talking about the things that destroy our cutting tool and how a high efficiency tool path, as we've said over and over and over, dynamic, adaptive, profit milling, these high efficiency tool paths take care of our tools. Well, the two things that we really need these tool paths to take care of is heat and vibration. These are the two things that are going to kill your tool quicker than anything. That's what starts deteriorating the tool. Once the heat gets into it, it starts destroying it. And once it starts vibrating, carbide's very brittle, it starts breaking. So we're going to talk about on this episode how we control the heat first, and then how we control the vibration. Now I say how we, but we don't do it. The tool path does it. We just put the tool in the best situation. So we're going to talk about that starting next. So the first thing we're going to talk about is heat, right? We want to control the heat. So a dynamic tool path controls the heat for us. Well, how does it control the heat? Well, let's just step back a little bit. We talked about angle of engagement on the last episode. If you haven't watched it, go back and do it. What we're trying to do is minimize the angle of engagement on our cutting tool. How do we minimize the angle of engagement? Well, we minimize the angle of engagement by taking a lighter radial step over. Now, when we take a lighter radial step over and we minimize how much of that material is in there, and we take a look at this, and let's just run through it. If we take a heavy step over and we're running, say, 6 flutes, 7 flutes, each one of those cutting edges is in the material for a long time. It generates friction. Friction is our enemy. If we generate friction, we generate heat. So if we start backing off the radial to step number 2, our cutting edge is in the heat zone, in that heat zone before it gets out of there, less time. If you take even a lighter radial step over, now you're talking that 4, 5, 6% of that cutting tool, angle of engagement is smaller from the last one, and our cutting edge is in the heat zone for a little bit, and then it's in a cool down, could be coolant, could be running dry. It's in a cool down period, and then it goes back to the heat zone. This keeps the temperature on our cutting edge lower. If we can control the temperature of our cutting edge, then we can control how long that coating and that substrate can maintain before we start deteriorating it. So if you take a look at this, if you can see where we're in the heat zone here for a little bit, and then that's what is allowing our cutting tool to handle more friction because we have less heat there. So folks, just to give a nice little analogy of how it works, if we just take a look at heat in general, say something like this with a flame, okay? And I take my cutting edge as a finger, you'll notice that the less time I stay in the heat zone, the longer I can bring my finger past it, right? That's where when you're keeping that cutting edge in the heat zone, You can control it a little bit better because it takes a lot longer for my finger in this case to heat up. The longer I stay over the heat zone, God, son of a... Well, the point is, when we take a lighter radial, when you look here, that you don't have your cutting edge in the heat zone. It stays in the coolant a little bit longer than in the heat zone. That's a lighter radial. Angle of engagement controls that. A lighter radial also controls the heat at the cutting edge. Now, when we do that, and we take a lighter radial, what do you think we can do? We can accelerate our surface foot, our SFM. We can accelerate our RPM because we have less heat at the cutting edge. And when we accelerate our RPM controls our feed, right? Surface foot is RPM, RPM is feed, inch per tooth, therefore we can feed it faster. So the angle of engagement is controlling the angle on there. The light radial is controlling the heat at the cutting edge. We're bringing it down. We can elevate our surface foot. Surface foot is RPM, RPM is inch per tooth. That's our feed, and we can run a lot faster. This is how a high efficiency toolpath, by controlling the angle of engagement, by taking a light radial, we get to control the heat at the cutting edge. So now folks, let's talk about the vibration part. How does a high efficiency toolpath take care of the vibration? Well, if you go back to the angle of engagement in the video we watched before, when you run a traditional toolpath, it's all about a light axial depth of cut, a fewer amounts of flute, okay, and a heavy radial step over. Generates a lot of heat. We figured out how to take care of the heat. We go with a light or a heavy axial and a light radial. But when you go with a light axial in a traditional toolpath, you get one flute in cut, one flute out of cut. You're not stabilizing the cutter. Our goal to reduce vibration is to stabilize the cutter. Well, how do we stabilize the cutter? We need to put more than one flute in cut at all times. Minimum of 2 and probably a maximum of 4 or 5, but that's for another episode. So what we want to do is, by taking a longer axial depth of cut, lighter radial, what we can do is we can maximize how many flutes are in cut. This way, when one flute exits the material, there's another flute or 2 flutes that are in that material, so you don't get spring back. That tool is not springing back. And if you don't get that tool to spring back, okay, and everybody understands something. I know it is carbide, it's very rigid, but that tool is still under load and it is still deflecting. If we can stabilize the cutter by putting more than one flute in the material at one time, you don't get that spring back. If you don't get that spring back, you don't get vibration. And if you can stabilize that cutter, it's going to stabilize your tool when it's cutting. So the whole key to this taking care of heat and vibration is by taking a light radial depth of cut, taking a heavy axial depth of cut. We're going to add flutes, and don't forget, when we add flutes, we add core strength, and when we add core strength, we get even less deflection. Less deflection, less vibration. We're still taking care of that vibration. So we take that, we take a heavy axial, we get less deflection, we control the angle of engagement from the last video, and therefore our tool path is taking that condition and driving it everywhere it goes to make sure we have stabilized that cutter, we have reduced the heat at the cutter, and we can add as many flutes so we can run as fast as possible to get the highest MRR, material removal rate. That's what it's all about, so we can be most efficient at our machining. So folks, thanks for joining me on this one. We talked about heat and vibration, which has everything to do with the angle of engagement from the last one. Hopefully you understand a little bit better how we take care of that. If you have any questions, again, please put your comments below. I would much appreciate it. Come back for the next one, because what we're going to do is we're going to wrap this HEM up. I'm going to put everything together. I'm going to take a tool path and I'm going to dissect how I kind of walk through it in a high efficiency tool path: dynamic, profit, adaptive, eye machining, volume mill. I don't want to leave anybody out. I'm sure there's a lot more tool paths and names that are synonymous to being close to what that high efficiency is. come back for that. And I'm going to walk you through how I would select a tool, how I would select a tool path, and how I would actually machine this all the way through for high efficient. But before I go, don't forget, there's 3 guarantees in life we're never going to get away from: death, taxes, and spring passes. Have a great rest of your week, folks.